still offline? Yeah, live. Okay. Welcome everybody on our fourth class of the new course. My name is Tom. Third. Sorry, you're right. Sorry, I'm ahead week. I got number 3, so I just misread it. So my name is Tom Breza. I'm the host. I initially created the group, but I wouldn't be able because I don't know C++ myself. So I found really great people like Tristan and Oliver. And as it happens, that was pretty much exactly spot on a year ago. And obviously, we Polish people, we like sweet things. So what we did is we thought it would be an amazing celebration, and what wouldn't be better than have our own cake? It's a homemade, delicious hopefully cake, which we'll be sharing with everybody. So the good thing is you are very welcome to enjoy. Is anybody who is allergic to chocolate? Good. Okay. What I'm suggesting is to take a photo with everybody. Do you want to join me and we'll take the photo together? Can we ask one volunteer to take a photo?
Who doesn't want to be featured? Who's embarrassed to be here?
So if we can try, Tristan, Ollie, can you help me?
So all three of us hold it then?
Yeah, I'll grab this. Okay. So I'll just keep it so it will tilt a little bit.
Yeah. 3, 2, 1.
Jeez.
Let me do another one. There we go. 4.
If you want to replace, somebody else can swap you and you will be on the photo this way.
I'm a bit nervous about this. I hope it doesn't go.
Cool.
Thanks. All right. Dig in.
Thanks, everyone. So what we'll do, we'll start cutting the cake. Ollie, do you want to do the honor? I'll do the introduction. So
I like this, right? Straight down.
You can do the better job than that.
I don't want to destroy the C++, if being honest. I have a
So thank you very much, everybody, for coming. It's a pleasure to have you. And obviously, we'll try to teach you some C++ once we finish cutting the cake. For people who are new, we are twice a week meetup. How does it work? On Tuesdays, so basically today, there is a lecture. So you're coming, and we pretty much will do only explaining, like a lecture on university. On Thursday, on the other hand, we want you to come back and do the exercises. Yes. Why did we decide to do that? Simply because if you do a lecture and no exercises, when Tristan or Ollie explains, that sounds extremely simple. That's simple. No trouble at all. But then when you sit down on your own with IDE and you try to write the code, suddenly it's not so simple. And the only way to basically to get this ready into your head is by exercises. And so I would say exercises are even more important than a lecture, because lecture you can get from different places. But the exercises basically will give you the way to remember. So what we're asking you to do is, if you're going for the lecture, which is happening usually at Skills Matters or maybe at Mimecast, RSVP at Skills Matter website if it's for here. If it's for Mimecast, RSVP for our website. On the other hand, the workshops, which are happening pretty much custom the opposite side, yes, on the other side of the street, RSVP with us. Why? Because we want to ensure that there's at least one experienced developer who can assist you. If you're stuck, we want to know that it's at least one person. If we don't know, if we don't know who is coming or anybody's coming, the experienced developer, why is it not coming? Or if it turns up and there's nobody there, you might say, I wasted my time, thank you very much, I'm not coming ever again. So, Ollie, you have a question.
No, I was just saying, if I painted this yellow, it'd be Pac-Man. That's just a useless comment.
So, please do help us and do the RSVP. Workshops and meetings at Mimecast or anywhere else at our website. Anything else that's happening, Skills Matters on their website. If you want any up-to-date information, please do follow me on my Twitter. My handle is xxvms. And obviously go to our website, ctclondonuni.com. Now, very important, as you know, our project is run pretty much by volunteers. So we're not paid anything. Yes. But unfortunately, Tristan MacBook decided to pack down and it's not working. So we are collecting, we're doing the GoFundMe page, so hopefully Tristan can get a new machine. So if you're benefiting from the classes, you help us. Another thing which I want to ask you a favor is like to break the official circle, yes? We won't get the sponsors unless we show that actually we make a difference in your lives. Yeah, somebody got a job, promotion, change their lives for better. And we can only achieve that with you. So if you have a success, if you're a success story, come back to us. Yes, we will put a section on our website with your photo and short story. How did we help you? Yeah, so this way basically we can make this project sustainable. So a year, 2 years, 5 years from now, actually this project will be running. Because we don't know how long we'll be able to stay here, and obviously we need to make sure that these amazing guys, they are paid some kind of money, yes, for their time. Getting in and out of London is like 20, 30 quid. So your help will be much appreciated. So that's all from the boring stuff. Now, if you need a license, email me, and I will send you a code for CLion license. And obviously, after our class, we're going to pub. So everybody is welcome to come to the class, to the pub, and buy these guys at least one beer. Yes, get them done and fed them. So without much more, please do enjoy your cake and some C++ class, and please make sure the class is spotless, the place is spotless, or the Skills Matter will have my head on plate. Thank you very much.
All right, good evening, everybody.
Feel free to grab cake, by the way.
Thank you all for coming.
Guys and girls.
Yeah, why don't we just do the cake thing and then I'll... Otherwise you're just going to be staring at that table, right, and not listening to me.
Sugar.
The cake is delicious, by the way, thank you, Tom.
Is it?
Yeah, it's very nice.
Was it your wife?
No, mine. No. My wife, she's a solicitor. She will serve the code, law of code, not the cake. So enjoy.
That's good.
It's a homemade. Let's go. One of the online students is quite angry that he didn't make it now. Scotty, we will eat a cake in just to tease you, and next time we'll tease you. Others for you guys or take? Take.
Has everybody who wants cake got the cake? No, not quite. You tried to resist, but it wasn't
Yeah.
quite.
It's too much.
Ollie, you ever want to give up C++, you could be a great waitress.
Great waitress.
You have an alternative, skill, yes. Very sought after.
Isn't it waiter? I don't know.
No, he meant what he said.
Okay, gender change included with that, yeah.
All right, well, I'll get the introductory stuff out of the way whilst Ollie's cutting the last of the cake. First of all, people who've been here for the last couple of sessions will have seen me, heard me advertising this. It's a brand new C++ conference taking place in Kent. It's happening in February. It's run by a friend of ours. It's going to be really great. So if you're interested at all in going to a C++ conference, I'd recommend going to that website, taking a look. I'm going to be there. Whether that makes it more attractive or less, I don't know, but highly recommended. So please do take a look at that. Secondly, who's here for the first time today? Okay, a few of you. Well, welcome. Welcome. So this, as you will have gathered, is the third session. So you've missed the very introductory material. But fortunately for you, all the slides from the previous weeks, or for the previous 2 weeks, in fact, going back a year, are on our GitHub page. So if you go to github.com/CPP London Uni, you'll see there are quite a few repositories on there. But the one's called Course Materials, in particular Course Materials Autumn 2018. They have the slides from the past 2 weeks. Also, if you want to listen to me some more, all our talks are recorded and on YouTube. So if you go onto YouTube and search for C++ London Uni, you can find our channel and you can see the talks, in particular from the last couple of weeks. So, for those who are new, I've said this the last couple of weeks as well, but it's good to reiterate. This sort of module, as we're calling it, is I'm calling it Initial C++. It's an introduction to C++. And as Tom said, it's a mixture of talks, me here talking, exercises that I will get you to do in the sessions, and homework exercises. And as Tom said, the homework part of it is important. Right? It's like learning anything, but probably the best analogy is like learning a musical instrument. You can go to the lessons, and you can go to a lesson once a week, and yeah, you'll improve a bit. But what really helps you get better is practice. If you want to get good at playing the piano, you need to practice playing the piano. You can go to your lesson once a week, and the teacher will tell you how to play a scale, but in order to really get good at it, you need to practice. And that's the same with programming. The only way to get better at programming is by writing programs. So, as Tom said, we're having these sessions on Thursdays. Really encourage you all to come along. It's not like this. It's not slides and talking. It's sitting around doing programming in groups or individually, but you can talk to other people, get help. So yes, please do come along on Thursdays. This is an introduction to C++. We can't turn you into a C++ expert, not in a few weeks anyway. But the idea behind this initial module is we'll give you enough information to get started so that you can go and carry on your learning by yourself. And then as we progress, we'll have other modules that are, delve into different parts of C++. Because it's a very big language, there's a lot to it. And the best way to approach it is by dividing things into small, manageable chunks. And this is the first chunk, or at least that's the idea. My standard feedback slides, which a lot of people will have seen many, many times now. We like hearing from you. The best way to talk to us, or to talk to everybody, is if you join our Slack channel. So there's this Slack channel called CPP Lang, and in particular we've got our own room in there, which is, oh, that's wrong actually, that's the old one. Let me just quickly edit that. They very wisely changed the name just to CPP London Uni. So if you go to that URL, you can register on Slack. You just need to put your email address in. It'll send you an invitation. You just click the link, and you can join us on there. So if you haven't already done so, please do. Right. So last week, what did we talk about last week? We had a bit more of an introduction to C++. We talked about some commonly used types, integers, standard string, standard vector. We talked about declaring variables. We briefly touched on consts. We didn't actually manage to get as far as type deduction, but I put that on there anyway. This week's going to be a bit different because we're not actually going to learn any new C++. Well, the aim for this week is firstly to get you set up with a compiler and an IDE so that you can go and you can do this practice that I've been talking about. Yeah?
Will that include writing makefiles as well?
No. No, we'll get to build systems in a bit. So we want to get you set up with a compiler and an IDE, an editor, so that we're all on the same page, so that you can go and you can write more complex programs than fit just on one box. And then we're going to talk, well, that looks like a lot, it's not all that much, but we're going to talk about how the compiler works, how you actually build C++ programs. Because it's a little bit different from other languages. So, first things first, getting set up for C++. So if you've been following for the last couple of weeks, we've been using this website called OneBox to write some example code. And OneBox is great. It just lets you write some code in a little box, click the button, and it runs. Hopefully, if you've got things right. But obviously, that's kind of limited. You can't write real complex programs on a website. You want to actually write some real code. And to do that, you need a compiler set up on your system. And to make life easier, we can use a program called an IDE, an integrated development environment, which makes it easier to write our code. You can just use a text editor if you're sort of masochistic, but using a dedicated program helps things like showing you errors as you're typing things in, gives you code completion hints, that sort of thing. So again, if you've done any sort of programming before, you're probably familiar with what an IDE is, right? Yeah? Hopefully. You don't care, you're all just full of cake going, oh. So the IDE we prefer is called CLion. There are quite a few different ones available, but CLion is what we like because it works on all three platforms that people are likely to use. So it works on Windows, works on Mac, works on Linux. It's a paid product, but they give you a free month trial. And after that has expired, if you're attending the course with us, you get a continuation license. So you can carry on using it for the purposes of learning while you're with us, which is pretty cool. You also need a compiler. We'll go into this a bit more, but there are three main compilers for C++. We're going to use either GCC or Clang, depending on your system. They're both very up-to-date, very modern, and either one is perfectly good. So, has everyone got their laptop? They're all set up and ready to run? Okay, time for you to follow some instructions. I'm afraid the text on this slide is a little bit small, but hopefully you can read that. If you can't, then let me know. But please do go ahead, follow these instructions to install a compiler. And once everyone's done that, we'll do the second bit, which is installing CLion. Apparently this is pretty common. I heard someone refer to this as an install fest. That a lot of these introductory courses do. So this is our install fest.
Anyone needs help, just shout.
Yes.
Install CLion by itself.
Okay, so CLion works with the Visual Studio compiler, but it doesn't support debugging. You can't use the
Yeah.
CLion debugger.
Do I have to start
So,
again?
sorry?
Do I have to start again?
You don't have to start again. If you download the compiler for Windows, MinGW, then you can tell CLion where that lives, and then it will be able to use that.
What's the difference between the different compilers available out there?
We will get to that after we've done this.
Who's already done this?
It's the cake you've.
One,
I went through the
two,
thing 2 weeks ago.
3,
Okay.
4. Okay, we've got 4 people who have done it.
Do you put sleeping pills in the cake? That's what it is. It's
We.
Yeah.
Spice. You just turn everyone into zombies.
Follow the Elon Musk example.
Told you to use cocaine.
Well, what do we need is if I've already got a compiler and ID.
You know what you're doing, and you won't need us to help you build stuff. Then obviously no. The reason we pick CLion is if you're just starting out, then if you've done CLion and you have a problem through the course, we can just come and just help you very easily. If you have environment issues and you're using something completely different and you can't solve that yourself, then we might be able to help you. It's a lot easier for us because CLion essentially.
The other advantage is that CLion has good support for a build system called CMake, which is more or less kind of the standard, the most common build system that's used for C++ projects. We'll get into exactly what a build system is in a bit. So CLion has very good support for that. The very latest version of Visual Studio also supports it, but doesn't work quite as smoothly as it does in CLion.
It's pretty good actually.
Last time I used it, you had to fill out variables in JSON files to exactly tell it where libraries were and things. No, okay. Hi there.
Although with that said, I mean, if you are going to use Visual Studio anyway, you might as well just generate a VS project, a VS solution from CMake rather than trying to wrap it.
Yeah.
The CMake GUI is easier if you do have stuff that you have to configure manually.
Hi.
Have you ever tried Code Anywhere?
Code Anywhere? I've not heard of Code Anywhere. You have?
I have. It's an interesting product. I'm not quite sure how well it suits C++, given that, like for certain languages like Java, right, you just compile it once and run it everywhere. Whereas with C++, you compile it, you write it once. So Java has the model of write once, compile once, run anywhere. C++ has the model of write once, but you have to compile it separately everywhere. So it doesn't translate quite as well. Because if I can make a Java app and I'll build it and then it just runs on Windows or Linux or Mac. But if it's C++, I have to build it for Linux and build it for Mac and build it for Windows.
So I was expecting to hear lots of typing going on, and I can't hear any. So does that mean everyone's done?
It's too quiet.
Yeah. Is anyone still working on this?
Has anybody not done this?
Well, I'm going a different route. I'm going to the make file and stuff because of my system is just. But I'll catch up with you guys. If anything. It's not anything pressing.
Make files are terrible, by the way.
I know.
The-
but
yeah, the
it's
first
just-
one.
I've got G,
It's heavily
GCC
compressed,
and
takes a few
make file.
minutes.
Trying to get. I mean, I've done some C++, but that was years ago. So
Okay.
just
So generally,
I've got to read
if you can get CMake to work as a start, CMake's pretty lightweight.
Okay, well, since everyone's gone very quiet, hopefully everyone has done this step. So let's go on to installing CLion, which is actually very easy. If you haven't already done it, you can go to that link, jetbrains.com/CLion. There's a big button on there saying start my 30-day trial. It'll download it for your system, whatever appropriate format. You can run the installer, and then once that's done its installation, it should come up with a window, or you might have to click run CLion. The first time you start it, it'll guide you through the process of installing what it calls a tool chain, which is basically you need to tell it where the compiler lives. So for Mac and Linux, if you followed the previous steps, it should automatically find your compiler and everything else that it needs. For Windows, you need to tell it wherever you decompress that archive.
File before you show it's extracting, is that correct?
Yes, yeah. So if you download if the Windows installer for the compiler is very, very compressed fast, it takes several minutes usually.
If I were to install it to my package manager, there's like 10 different options for there's like CLion, CMake, EAP. Is there like
Are you using Arch?
yeah, can I just use one?
What's it? CLion?
I'm just wondering if we need a certain like build.
I think the EAP one is the like beta version of the beta of the next one.
Yeah, I just grabbed CLion. Hopefully you don't have CLion, you don't have CLion.
What do you think the pie means on the bottom of the stickers?
I don't know. It's just in.
Just go, you know who I am.
No,
I'm the guy in the hat.
No, it's just more like
To use
it's
Face
literally
ID.
part of the thing. Like, oh, okay. So, oh, yeah, you decided to do it.
And C++, is there a difference between using it on CentOS or Ubuntu?
Using
C++. Yes. On CentOS or Ubuntu.
there won't be any difference in using it. The commands to install the compiler will be decided to use the package manager.
Go back to clear.
Yeah.
It comes clear.
So I was reading last week's slide. One of the notes says don't use raw rates like C categories. What's the reason? What's the brief reason? What's the brief synopsis?
Same job, because if you have a raw C array, it's got 5 elements.
Can you find them?
I can tell it to access the 6th element, and it won't stop me. It'll just crash.
Okay.
Really?
Yeah, really.
Okay, so did you
Try it. Make an element 5 elements. Access 100. It won't harm your computer.
Well, so ask it to fetch a 5th element in the array that doesn't exist.
Or the 100th element, right?
Or whatever.
Whatever, yeah. So if you use something, instead if you use std array, now it's taking up exactly the same memory, it's emitting exactly the same CPU instructions when you compile it. But if you go out of bounds, it won't even let you compile. The compiler goes, oh no, can't do that. It's too fast.
Oh yeah, like calling something that doesn't exist.
So you're using wrappers basically introduce compile time save differently. But part of the power of C++, of course, is that it does still work with C. Right? It gives you a way to take very nasty, dangerous C libraries, wrap them up, and make them safe. So all of those nasty features are still have to be thwarted, because that's one of the key wins of using C++. Is you can take nasty C stuff and make it safe.
Yeah. Right. So if you install CLion.
So if you use raw array, then say you've only got 3 elements and you call 100 one, you'll get stuck in a loop.
No, it will compile to. Okay, so legally speaking, standardly speaking, computers, the compiler could admit anything, and when you run the program, it will just delete your hard drive. But it's not really likely. What it will do in practice is it will emit the instruction that accesses 100 bytes down, however many sizes, 100 elements size down in the memory. But the amount of memory you have allocated, if it's on the heap, for example, then generally speaking, the OS says that you're allowed to access this range.
Steps while you're
And when you go beyond that range, it causes, at least on Intel, right, to generate a CPU exception, which is an illegal access. You're trying to access an address of memory, you're not allowed to access it because the OS didn't give it to you. And then the OS goes, oh,
I'm aware of what it is.
this program tried to access memory that I didn't give him access to. Anyway, that's a crash.
That wasn't very energetic, so he put it on a robot arm. And apparently he was over 60 kilometres one day.
You sure it died? Because when it's done, it just sort of disappears, but the files are extracted.
Okay, well anyway, I've got the
Did you hear how the new iPhone XS Max not charging? They have charging issues. Some of them have charging issues and out of the box it'll drain and that's it. It's not finished. Doesn't bring this disposal. Some of them it will you plug it in won't recognize the charge. And one of them, another variable is you plug in the charging, you turn on from sleep, turn on the screen and
The pilot package doesn't actually install anything. It's start
Why Apple?
It's just got this way to
wherever you download, wherever you download it.
so the Emperor is hiding away somewhere.
I'm sure that's the excuse they would use in the press release. Just like, iPhone 4 and everything out. And the antenna, they said, oh, it's meant you holding it wrong. It's meant to be holding this.
Yeah, because that's a valid excuse.
Looking at it. Don't blink.
That's ridiculous. Overpriced tat.
So there's a YouTube tech, YouTuber. He did sort of a sample. He took 8 iPhones, the XS and the Max, and only one function does it. So 7 out of 8 had those defects.
Whichever file sets first, I'll come to the file or something. Between 2 locations.
We'll just change it.
I've done the dates. I've done it by date. I won't necessarily have the same dates. So, okay, what sort of name should I be looking at?
So just scroll down. You could just install it to see.
See what's in there. Unfortunate name. So should have extracted something like C.
Yeah, I don't know what happened.
Maybe I could just copy it and move that and sit in another folder.
I already found out when she was saying
Have you done much programming? Yeah.
It's already gone. Went to this office file.
So what's your background? Why did you decide to start with video?
I'm doing entries.
Sorry?
I'm doing entries. People that were in Dawn. They always tinkering and doing stuff like that. I couldn't find anything like it.
Why is it something? And how do you link up with Tristan?
We went there just while I was back from Australia. He was work over like he was lucky.
That was a good one. So you could highlighting some other stuff.
Yeah, if you got that kind of stuff.
Yeah, there's no plus. It's very much very good asset. Just just the fact that what is it anything that you want to
Could be extremely dangerous. Once this is done, you go to that one. It's really, really interesting. I think it's once we install it's like a computer. So
Yeah.
Are people still saying things online?
Builder.
there's very cool stuff. How you can overlay
No.
so you can make it equal side front of it, things like that. Yeah, so for example, if you do
Well done, all good.
matrix maths and things like that.
Most of them.
Stuff for you. Just to come up with a sensible. Oh, not sensible.
We'll test it in a minute, so just wait there.
There's a central line strike this week for 24 hours on Friday. Central line, 7th of November. Not this Friday, 7th November. There's going to be a 24 hour central line strike on a Friday.
No, somebody.
That's fine. I believe in computer. It's absolutely fine. Just reading stuff.
Oh yes, good way.
Yeah, because I did it myself. The only thing to do is change the settings on the file.
Okay. Hopefully most people are there. If you're not quite yet, then just hold on, and if you follow the instructions, it should all be working. But let's have a very quick test to see whether everyone's got set up with CLion, and then if anyone has any problems with this step, we can sort you out. So first of all, when you launch it, on the Mac it looks like this. You may not have all these things at the side. That's obviously because I've been using it for a while and it's got all my old projects. But you probably have a window that looks like this. So just click New Project. We want to make sure it says C++ executable up there. You can change that down to 14 if you want. And see, it picks a default location for you. This is was the last place I created a project. You can call it whatever you like. What should we call it? We'll just call it Session 3 example. And then click Create. And it'll think for a while. Oh, it's popped up on my other monitor. Just wait a while. So hopefully, if you follow that, you should get a window that looks roughly like this. Your toolbar buttons might be in a slightly different place. I've been upgrading from older versions of CLion, so it's still got an old config, but your toolbar buttons might be in slightly different places.
Create a new project.
Sorry? Create a new project, yeah. And then you want the project type to be C++ executable. Yeah. So if you've done that, this is taking its time because my computer's busy doing other things at the same time. But hopefully, so while this is thinking, who's got that far? Put your hand up if you've managed to create a new project. Yeah? Most people. Yeah, this process of doing the background task is annoying. But it's not usually this slow, it's just because my computer's very busy sending things, uploading the whole course to the internet as we're doing this. So. Rather than everyone just sitting staring at my laptop, if you, once it's finished doing its background tasks, you should find a green button on the toolbar that looks like a play icon. Everyone see that? It's grayed out for me because it's still doing its background stuff. But for me, it's there. I think on new installations, it puts it over on the right-hand side. So if you just click that, then fingers crossed, it should think for a few seconds and compile your program, and then it'll pop up saying hello world at the bottom. That's the idea. We're apparently going to have to wait forever for my computer to do its stuff. Hello world. Awesome. Hello world. Brilliant. How are you getting on over here? Yeah.
Could be a little
Okay, so you've installed CLion, you have to just configure it so that it can find configure the tool chains. You haven't done that before.
I can just press on the blue.
Yeah, once it's finished doing its extraction, speaking of things taking a long time, this appears to be taking forever. So. Okay, so who hasn't managed to compile the Hello World program? So that's an easy way to do it. Okay. Sorry, so done with all settings. So you want to evaluate for free? Yeah, so if you keep on coming to our sessions, we'll give you a so a new project. Change the title from the name from Untitled. C++ 14 is fine.
I'll install though, you can see. Yeah. Straightforward, yeah.
I'll show you for free.
Yeah, I've read them. You've done the program. Okay, did you not C++? Oh, okay.
So do you mind taking forever to do this? It should be quicker on most people's computers. Okay, so
Okay, so
your project is
I don't think we're going.
I'm not sure of any way to change it once you've decided. Because that's like where the directory in which the project lives, so you'll have to rename that directory. I don't think
That's why I was looking professional.
I don't think there's a way to rename it.
Okay. So your web yeah.
I think once you've decided.
Yeah,
Oh yeah.
well, no, I'm doing not professional programming full time now. I started last year, and then went on to React Native, wrote Android app.
You got it now.
Then I now this year got more into 3D graphics.
Yeah, this is what mine is.
It seems very interesting, so, but I haven't made any money yet.
No,
It's I'm struggling with lighting, yeah, 3D lighting.
so once that pre-run yes, once it's finished, then once that
Yeah.
Anybody need some help?
Raise your hand.
Yeah,
if you need
that's
help.
finally finished.
Yeah.
Yeah. So, okay, so hopefully on your toolbar you'll be able to see a play button. If you haven't done this already, press it. You should get something like this turn up. Again, my computer's been particularly slow this evening. And for whatever reason, I have not got Hello World pop up, which, you know, is great. There we are, that's better. Hello World. So hopefully everybody has got that far. So let's get on with the show. Is everybody happy that they're all set up and ready to go? This is quite an important step, so that's why we're spending some time making sure everybody's here. But I think everybody is now. But if you're not, then do let us know. So let's talk about compilers for C++. There are lots of them available. But these days, there are three that matter. There's something called GCC, stands for the GNU or GNU compiler collection. So if you're familiar with the Free Software Foundation, they have this set of compilers for a variety of different languages. They're under this GCC banner. For obscure reasons, this is called MinGW on Windows. Careful how you pronounce that one. We've already had a... Yes, so that's a minimal GNU for Windows, but yes. So that's one of the main ones. The other main one is slightly newer than GCC. It's called Clang. This is part of the LLVM project. So LLVM is kind of an underlying technology that powers a lot of compilers. So if you use Rust or Swift or I think Go as well, they're all built on top of LLVM. And Clang is a C and C++ compiler that's built on top of LLVM. So Clang and GCC are the two really good ones. They're really up to date. They follow all the new C++ standards. They're both fully C++ 17. Clang and GCC are both really good. The third important one is the Microsoft compiler, Microsoft Visual C++. So if you install Visual Studio, you'll get, well, assuming you install the right packages for Visual Studio, you'll get MSVC. MSVC is, well, it's not quite as good as the other two, to be perfectly frank. In fairness to Microsoft, they're investing a lot, they're spending a lot of money, putting a lot of developers on trying to catch up to the first two. But there are still some things that MSVC can't do or doesn't do quite as well as the other two. But nonetheless, it's still pretty important to use by many people because it comes with Visual Studio, and Visual Studio is sort of the standard IDE that people use on Windows. So this third one, it's catching up. It's not quite there yet, but hopefully in a year or two it will be. So for this course, we recommend using either GCC or Clang. And if you follow the instructions from just a little while ago, you will have installed one of those two. So Clang is the default compiler on Apple systems. GCC tends to be used on Linux, and you can also get GCC for Windows. You can get Clang for Windows as well, but unfortunately CLion doesn't support it yet, which is why we tell you to use MinGW. All make sense? Awesome. So now we've installed something called a compiler. Great. What is that?
So it converts the text into binary so the computer can execute zeros and ones.
I didn't catch the last bit, sorry.
So it converts into a binary. All of your text, all of your program that you can read and reread, it converts into zeros and ones, and then so computer can execute it.
Well, I'll tell you, there's no point in me being here, is there? Yeah. Slightly more generally, if I'm going, I mean, that's a fantastic answer in the context of C++. Slightly more generally, it's a program that takes your source code, your text, and converts it into some other form. So, for example, if you have a Java compiler doesn't output machine code, it outputs something called Java bytecode that runs on the JVM. You can have a C# compiler that outputs, .NET, CLion, yeah, that's the one. But for C++, the compiler is a program that, exactly as you said, takes your source code and turns it into machine code, which is just a list of instructions that are executed directly on your CPU. Because it's executed on your CPU, it's typically specific to the kind of computer you have. That means you can't just take a C++ program compiled for a typical Intel system on Windows. You can't run that on an iPhone, for example. You have to recompile your source code for a new system. Okay, so iPhones or most mobile phones have ARM processors, most desktop computers, most laptops have Intel processors. These use different CPU instructions. So you can't just take the machine code that you've compiled on Windows and run that same executable on a different system. So this is a little bit different from other languages you might have used. If you used a higher level languages, something like Java, you can generally take the bytecode and run it on a different system. But for C++, as with C, as with other low-level languages, what they're called native languages, we have this machine code, so we have to recompile our program for different systems.
So it doesn't go through the assembler stage?
It does, but that's all sort of hidden from you. Okay. The compiler will output the machine code for you. So an assembler will take assembly instructions, so you can get the compiler if you give it the right options to output that for you, but it's generally done as a hidden step. So, as I said, it's a compiler's job to translate your source code into machine code, or a C++ compiler's job. And the first thing it does is it checks the syntax of your code. That is, have you used the symbols, the names, the words in a way that it can understand? So if you think about this in terms of sort of natural language, it's whether you've spelt things right. Like, can I understand what these words are? Can I understand the punctuation you've used? Okay, so if you are expecting English text, but there are lots of Chinese characters in there, then an English reader is not typically going to be able to understand what those characters mean. So the syntax is, have I spelt things right? Have I used the right punctuation? It also, to some extent, checks the semantics of your program. That is, does it make sense? Tries to understand the meaning of what you're trying to do. So the second part would be, it tries to check whether the types you've used are compatible. Is it okay to pass an argument of this type to this function? Right, so the syntax would be, do I understand that you're trying to call a function? Semantics, or the type checking part of it would be, can I call this function with this argument type? If either of these stages fail, you'll get a compiler error. That is, literally there will be a message saying, error, I couldn't understand what this is. And unless something really bad has happened, you will get usually the line and even the column of exactly where the problem is. So in CLion, or most IDEs, in fact, if you get a compile error, get a message, you just click on it, and it will jump your editor to exactly where the problem is, which is really good. C++, as I talked about in the last couple of weeks, is a strongly typed language. Every variable, in fact, every expression has a particular type. And we can only do things when types are compatible. And the reason behind this is that we strongly, in the C++ world, strongly prefer compile time errors. There are other languages that go even further. So Rust goes much further than C++ in terms of trying to make every possible mistake in your program into a compile time error, rather than something that happens when you run your program. So this has a lot of advantages. If you're familiar with Python, for example, you can have a Python program that, syntactically is fine. It's not until you actually try to run a particular function that you'll see an error message come up saying, couldn't do this with type none, or whatever the error message might be. Whereas in C++, hopefully, that would manifest itself as a compile error instead. And the reasoning behind this really is that in an ideal world, you'll compile your program once, or you'll compile the final version of it once, and then somebody might, you might run it 1,000 times, 1,000,000 times. So if we can move things from happening when the program runs to when the compiler runs, that's going to be a tremendous advantage. And in fact, C++ has a lot of facilities these days to be able to do entire calculations at the time that the compiler runs to save you from having to do those calculations when the computer runs. That's a facility called constexpo, which maybe we'll talk about sometime down the line. So once the compiler is checked, your program's checked that it understands it, it begins this process of translating it into machine code. And it will usually apply various optimizations to make things run faster. So, in a simplified sense anyway, there are sort of two modes. There's what we call debug mode and release mode. And in debug mode, the computer doesn't put in as many optimizations, but it means that when we run the debugger, which we'll have a look at in a bit, when we run the debugger, it means we can step through our code easily. It means the generated machine code has almost a one-to-one correspondence between our source code. So as we execute the machine code instructions, we can look and see, okay, that corresponds to this line in our source code. Which is really useful for if you need to step through your program in the debugger, you can see exactly when a problem might have occurred in your source. Which is great. Unfortunately, doing that is not necessarily very fast in terms of runtime speed. When this is C++, we want everything to be really fast. So when we have checked that our programs are error-free, we will compile them again with these optimizations enabled in what's called release mode. And then typically, we can't then use our release binaries, our release code, our release versions of our executable. We can't use those in the debugger because the information is no longer there. There's no longer a good correspondence between what we wrote and what the compiler has generated, because it's applied these optimizations. It's done very, very clever things to make your code do the same thing, but do it much faster. Does that make sense? Yeah? Few nods of heads, yeah.
How much faster is faster, like debug to release?
It really, really depends on what you're doing, but it can be of the order of thousands of times. I mean, it's hard to put a figure on it because it really depends, but for a lot like heavy mathematical calculations. If it can do what a process called inlining, it can speed it up, 1,000 times. Tens of times faster is very common. Really does make a massive difference. So how do we run our compiler? Well, we just saw a way of doing it through the IDE. But if you're an old school Unix person, if you like the command line, you can just invoke the compiler like this. It's just a program on your system that you can access via the terminal. So on Unix systems, this is a capital C for the C++ compiler. There's also a lowercase cc, which is the C compiler, but we want this C++ compiler, so this is capital C's. And then you tell it the name of the file that you want to compile. This is just a text file with the extension CPP. And then you give it -O, and then you tell it the name of the program, the name of the output. The -O specifies the output. And actually, just doing this is really useful for little test programs. If you've just got 10 lines that you want to just check, is this okay? Well, you can either use OneBox, it's really useful for that, or another site that's very common is Godbolt. But you can also just do it locally. You can just create a text file in Notepad or whatever and quickly ask the compiler, can you just compile this for me, rather than having to go through all that rigmarole of creating a new project.
So is that actually an artifact that it's producing?
This is an executable, like a program you can run on your computer.
The jar file.
Not like a jar file exactly, because a jar file has to be run by the Java runtime. This is a program that you can run. A binary file, exactly, yeah. And you can also, so this is the Unix version with, or macOS with the capital CC. You can also use exactly this form on Windows. You just have to write g++.exe. But you can use the Windows, the command prompt, if you really want to do that. I did have a little exercise to get you guys to just try this out. You can do that if you like, just using Notepad or something, but we're a little bit behind time, so I reckon we're just going to skip this. If that's all right with everybody? Yeah. Just imagine you've practiced invoking the compiler. So, schematically, we take our source file, we give it to the compiler, and the compiler gives us an executable. Pretty simple. Yeah? Hopefully. People are worried about this. Are you just worried about where this is going? Is that why? Is that why what the trepidation? We can also pass multiple files to the compiler at once. So, on the command line, we just gave it the name of whatever I called it, myfile.cpp. You can actually give it multiple source files and then do the -O to tell it the output name. So we can send multiple files to the compiler at once, and it'll compile all of those, link them together, and form this executable. That's great. But is it? In real-world programs, when we have a big program, we can have dozens, hundreds, thousands of source files. And we don't want to send all of those to the compiler at once, typically. There are advantages to doing so, but usually we don't want to, because it takes a very, very long time. If your compiler is trying to compile thousands of source files in one go, that's going to take a very long time for it to process. And I mean, in a really big project, if you're talking like a typical PlayStation game or something like that, compiling the final release build can take hours, right? Purely because you've got millions of lines of code that the compiler's trying to process, trying to optimize, trying to turn into your executable. So this is not really practical to do every day, everyday editing. You don't want to just, oh, well, just try this out. What if I do that instead? And you change 2 lines and you press the button and then you go and wait an hour. That's not conducive to getting work done. So what we want to do is something called separate compilation. And what we do is we send our files to the compiler individually. And each source file it's sent to the compiler by itself. And the compiler produces something called an object file. So rather than an executable coming out, it produces this intermediate thing called an object file that contains the compiled code, but it's not the finished form. It's part of a program. It contains the objects in your program. And then a second program, well, in fact, it's the compiler, but running in a different mode. Same executable, but running in a different mode. It's called the linker. And it takes your object files, takes your intermediate files and links them together into your final executable. So again, this is rather different to, I mean, it's the same way this works in C or in Fortran. It's a bit different to how it works in most other languages, which is why I'm spending today kind of going over how this model works. Just a little bit different. So we have this idea of separate compilation. So schematically, we look like this. We take our source file, we give it to the compiler, it produces an object file. Take our second source file, we give it to the compiler, it produces another object file, and so on. Dozens, hundreds, thousands of times this can happen. And we have these object files on Unix systems. They typically have a .o ending. On Windows, they tend to give them .obj. And when we finished, when we generated all our object files, we hand all of those to the linker. And this linking step, because these are binary files, it doesn't have to parse the source code, it doesn't have to do the optimizations. All that's happened already. All this has to do, as we'll see in a minute, is resolve your function calls, work out that, okay, this function is calling a list of instructions that were in this other object file. It links them together, and from there, it creates your final executable. So it's like a 2-stage process. First we compile, then we link.
And where the libraries would be added? Would be added in the linker or prior to that?
That is a good question.
Okay.
So it's rare that we can write our program and not make use of any other code at all. So we have these repositories of software that other people have written. We call them libraries. So again, if you've done any sort of programming whatsoever, you'll probably be familiar with the idea of software libraries. And the way libraries are distributed are as object files, more or less. And so we take our pre-compiled library, and we take our code, our object files, and we hand all of those things to the linker. And then the linker mixes together our object files, the object files from the library, and from there it produces the final executable. Yeah?
Why don't you check if some library is missing? So you say include, and then you say the library. Then if the library is not in the system,
Compiler.
So we'll see in a minute, there are 2 parts. You need the header files for your library. And so if those are missing, then the compiler will complain. But if you've got the header files but not the compiled objects, then the linker will complain. We'll say, I can't find a definition of this function.
this is already the execution code. So it's already the code basically that will be passed to the linker is already the code
actually will run against them.
That's exactly. So that's the machine code.
The machine
Yes.
code.
Yes. So if you think this library stuff sounds a bit esoteric, you've actually already used one. You've been doing the examples without realizing it. C++ comes with a library built in. It's called the standard library. And it's bundled with your compiler. And when you write a C++ program, when we did our very simple step, that little 3-step thing, it was automatically linking in the C++ standard library. We didn't have to do anything. That happened automatically. But we can use other libraries, and we have to tell it which libraries we're using.
What standard library contains is just the types of variables, or?
So the standard library contains a whole load of stuff. In particular, it contains some very useful container classes. So vector is a very important one. String is another one. It contains a lot of very useful functions. So one that we've seen an example of is a function that's in there called toString, which takes whatever argument, might be an integer, and it creates a string that so you give it an integer of 0, and it will hand you back a string representation of 0.
Isn't it?
Sorry?
Sleep or microsleep as well.
Sleep, yeah, all of those things. It's got a whole load of threading functions. If you want to write multi-threaded code, has lots of quite low-level algorithms. It's a part called the STL. Yes.
I have a question. So the library objects, will they be sort of created at the linker stage, or does the linker always have the objects ready?
So typically what will happen is that you will have downloaded your library from somewhere, or maybe you will have downloaded the source code for that library and compiled it yourself somewhere, and it will be sitting on your hard drive. And that compiled object code will just be sitting there ready to be linked into a final program. So this looks like it's much more complicated than it needs to be. But this has a tremendous advantage. That if we change this source file, we only have to run this instance of the compiler to generate a new object file here. If we haven't changed any of these object files, and remember there might be thousands of them, if we haven't changed those source files, then the object files aren't going to change. So this idea of separate compilation means that we only have to recompile the source files that we've changed. So this can take your hours of compilation time down to a few seconds, which, again, as we say, if you're trying things out, if you're compiling things dozens of times a day, this makes a massive difference. And it's kind of what makes C++ vaguely practical for real projects. If we had to compile all our thousands of source files every time, we'd never get anything done.
Sorry, are your libraries per project or per CLion?
Per system. So, or more or less. So you will compile your library for Windows Intel, for example. And you'll usually compile the libraries in release mode because you want them to, you're not responsible for that code, you're not debugging that code, you just want it to run fast. So you compile them in release mode, and then that object code is there, ready to be handed to the linker to generate a final executor. Yeah.
Are these libraries compatible between the various IDEs? In other words, this one we're calling, say, include IOStream. If I put that in another compiler, would it recognise IOStream as being a library it's got?
Yeah, so the IOStream is part of the standard library. So that's the one that comes with the compiler. So you can guarantee any C++ compiler will have this standard library because it's standard. So that's one you don't have to go out and get for yourself. But there are other libraries. There's a very common set of libraries called Boost. So if you wanted to use that, you'd have to make sure you had a copy of Boost installed. And in fact,
they're all compatible between the various IDEs.
It's not the IDEs. The IDE just runs this other program called a compiler.
Right.
Okay, that's why.
And Okay, compatible between the various linkers then that come with the
Uh,
IDEs.
Sadly not. Okay, so the situation on Unix systems, yes, it all works together, and that's very happy. For Windows, it's slightly more complicated. In fact, it's quite a bit more complicated. But basically, the object files that are generated by Microsoft Visual C++ are not compatible with the kind of object files that are generated by MinGW, by GCC. So you have to plump for one or the other. You have to compile all your. You have to use one compiler for both all your source files and for all your libraries. You either have to stay in the Microsoft world or you stay in the GCC world. And often, if you go and look on websites that offer you pre-compiled libraries for Windows, they will offer two versions. In fact, on Windows, it's even worse than that because different versions of the Microsoft compiler, 2013 is not compatible with 2015. Yeah. So on Windows, this is quite painful. On Unix systems, on a Mac, on Linux, it works a lot better. Yeah.
If I create my object files and let's suppose that one object file will call another object file, the functionality of another object
Yes.
file, and the object file that's calling exists, but let's suppose that the function has a different signature, for example.
Yeah.
Would the linker detect that there's an error there, or it will?
That's a good question. So how does this source file know about the functions that you've declared in this source file? How does it know the signatures? How does it know the right types, whether it can send these types? I've said that the compiler does all this type checking for you. But since we're sending all these individually, how do we use the information in there? We actually use something called header files, which I'll talk about in a minute. First of all, let's have a brief chat about build systems. So that last diagram I showed, time to go. The last diagram I showed is pretty complicated, right? No? No, fine. Okay, simple. You can imagine, I just showed 3 source files. If you had several thousand in there, trying to work out which particular one has changed. If I'm editing lots of different files, trying to work out exactly which one has changed, trying to give the right command to link this particular version of the library to my program, all that gets pretty tricky. And so, in most compiled languages, we developed these programs, build tools, build systems, to manage this process for us. So, on Java, for example, Gradle is pretty common. C# programs, there's MS Build, which is the one that's used by Visual Studio. We use these in C++ as well. And they take care of noticing, noticing which files have changed, which files have edited, and working out which object files we need to regenerate. And there are many, many, many different ones out there. So that's, what's that, 5? I could easily have listed 20. There are lots of them. Fortunately for us, the C++ world has mostly, not entirely, but mostly decided to plump with something called CMake. And CLion, one of the reasons we use CLion is because it has very good support for this CMake build system. So in general, we won't be manually editing our build files or anything like that. our make files that you were asking about.
I have created one anyway.
You've created one anyway.
Yeah, the kids support system, but
Well,
it works.
so one of the things that CMake does, CMake's a sort of higher level build tool, so CMake will generate a make file for you, which make then runs on a Unix system. You know, if you're on Windows, it'll usually create an MSVC project or a Visual Studio project file, which Visual Studio can understand. This is a C++ course, it's not a CMake course, and to be honest, I'm not enough of an expert in CMake to stand in front of a bunch of people and try and tell you how to use it anyway. I know just enough CMake to let me get stuff done. CMake is a very, very powerful tool. You can do crazy things with it, apparently. So I know just enough CMake to get stuff done. The whole CMake definition lives in a file called cmakelists.txt. So if you look at the project that you created, you will find there'll be the source file, which I think is just called main CPP. There's also a file in there called cmakelists.txt.
Sorry, but when we write a program, do we have to create this file, or will the compiler to automatically create this?
This is one of the reasons that we like to use CLion, is because CLion, the IDE, handles CMake for us. And I'll show you an example in a few minutes. So, fingers crossed, 90-something% of the time, we don't have to worry about this. We just say to CLion, please create me a new file, and it'll handle telling CMake about it, and then CMake will go and run the compiler for you. And it all works automatically. But if you're, as I say, if you're curious, you can have a look at this, you can edit it, you can play with it, you can read about CMake online. The documentation is not brilliant for CMake, unfortunately. Which is one of the reasons I've never really learned in depth how to use it. But the best way, if you're struggling with CMake, the thing that I've always found is I just type it into Google and I'll find myself on a Stack Overflow link, a Stack Overflow question, which is normally asking exactly what I want to know. So if you do ever get stuck with CMake, I just Google for errors.
So who's responsible for development of CMake?
It's a company. It's a company called Kitware. It's an open source project, but it's developed by this firm called Kitware. I don't know. I presume it started out as it's one of these things that started out years ago as a kind of proprietary thing. And
some American medical association thing that was the first that used this thing. It came spun off from them.
Oh, well, there you go. That's
it's a very complicated thing.
Yeah.
Is there any reason people didn't develop like a really good, manual and documentation for such a powerful project?
Yeah, that's a good question. There are now apparently more resources available now that it's become so widely used. Unfortunately, I don't. Yeah, sorry.
I'd like to point out I've had to deal with a lot of CMake. If anyone reads about this, there was a point where they sort of switched from old style CMake to new style CMake. So whatever you do, learn the new style. So the old style is very different and a lot worse. So the problem is you sort of have to Google for this the right way, otherwise you run into a trap.
But what benefits do you get over the normal standard make?
So CMake. So the trouble with make files is that they generally you have to kind of hard code the location of your compiler and the location of your files, and it's hard to write a make file that is portable between different operating systems. Right. So in general, you can't take a make file for Linux and just use that make file on Windows. It's not going to work. So CMake is a sort of higher level system that will generate the make files for you, except on Windows where it doesn't use make files, it uses this other project format. So it kind of abstracts these details away. So if you've done any Unix development, perhaps in C you might have used the GNU system called Automake, which is a sort of similar idea but very much worse. So Automake is horrible, but it does this similar thing of generating a makefile for you. And that's what CMake does. So yes, again, for simple projects, you can write your own makefile. And if that works for you, that's great. But for example, when I'm preparing examples, I couldn't just put a makefile in there, because then people who are trying to run my examples on Windows would have no chance. So CMake lets us write a project description in a way that's compatible with many different operating systems. Yeah, awesome. So let's turn our attention to something that's a bit weird in C++. Well, it's not unique to C++. It's something that's inherited from C and is kind of annoying, well, very annoying actually. It's something we've sort of learned to live with, and they're trying to do away with it, and perhaps if I run this course in a couple of years, there'll be a nice new shiny way to do these things much better. But for now, we're stuck with this sort of 40-year-old way of doing things, of splitting our code between what we call header files and implementation files. So, as we've seen, we like this idea of separate compilation, saying, okay, this source file hasn't changed, so I'm not going to bother rerunning the compiler, because the object file, I haven't changed the source, so I'm not going to change the object file. I can just reuse that same object file, and all I have to do is the linking step. It's much quicker. The trouble is, we generally want to reuse our types and our functions between our different source files. So how do we share information between different source files? Well, we have these special files called headers. So a header file contains the information, the declarations of your functions. It says there exists a function called something, and it takes arguments of these types, and it returns this type. It doesn't say what the function does, it just says this function exists, and you can call it with these types. And that information is sufficient for a second source file to be able to call that function, to know what argument types that function takes, what that function returns. It doesn't have to know any details about the implementation. That's compiled somewhere else. That doesn't matter. But it needs to know what we call the signature of the function. Its return type, its name, and its argument types. So our header files contain the signatures, what's called the declarations for our functions. And these are source code as well. So calling this actual files with the function definitions in, calling those source files gets a bit confusing. So we prefer to use the term header file, or I prefer to use the term header files and implementation files. So typically, the implementation files are the ones, well, no. The implementation files are the ones that get sent to the compiler. And we give those an extension .cpp. There are a few that get used. .cpp is by far the most common, but you might see .cc is also quite common. Header files aren't given to the compiler directly. Instead, header files are used to pass information between different implementation files. So you might say, well, this is a really silly system. Why do we have to do this manually? Can't we sort of extract the information about the headers and about the functions Can we extract that somehow from an implementation file? And yes, that would be lovely. It's quite difficult to do, but they're working on it. And as I say, hopefully in a couple of years' time, if I'm still doing these things, I'll be able to present another magic new slide, and all this rubbish with header files will go away, and it'll all happen magically. But for the moment, very unfortunately, we do have to manage this thing of header files and implementation files ourselves. Again, if you've done any C programming, you probably are already familiar with this idea. But it's really only C and C++ that have this sort of legacy thing of having to manage your code in two places. Yeah.
Is the relationship between header files and implementation files one-to-one, or
it
can
should
you find
be.
a header file and multiple implementation files for the same header file?
That would work, but in general, you want a one-to-one correspondence because it just makes your life so much easier. If you have like myfile.cpp and a corresponding myfile.hpp that has the declarations in it, that is far easier for you to manage. So on a sort of technical would this work level, yes, it doesn't really matter which source file contains the declaration. It can be anywhere. It's like the system doesn't care. It just needs to have a definition somewhere. But in a sort of practical, don't shoot yourself in the foot way, yes, having a one-to-one correspondence is what you want to do. So we typically place the function declaration. That's the information about what the name of this function is, what argument types it takes, and what its return type is. We place the function declarations into header files, and we place the implementation, that's what it actually does, we place that in an implementation file. So as I said, if the compiler has seen the declaration of a function, it knows how to call that function. It knows whether I can pass this variable into this function or not. And then later on, after we've got all our object files, the linker matches a call to a function from one object file to the actual code it needs to run. It links all those up. That's why it's called the linker. And we're talking about functions. There are actually quite a few other things that go in header files, but for the moment, we'll stick to talking about functions. Just make this a little bit more, it's not coming off, great. Let's make this a little bit more concrete then. Let's say we have a function it's called say hello. Function called say hello takes one parameter of type standard string, and the name is name. So this was actually an example that we used last week, the week before. And this function is going to return a standard string as well. So in our header file, we need to put the declaration of this function. So this is in the header. And the way we declare this function is we just write its signature, that is its name, its parameter types, and its return type. So we write this, and we just put a semicolon at the end. And what this is saying is that there exists a function of this name with these argument types, with this return type. This function exists. and you can call it. So then in our implementation file 1, we can say, so then if we have this line somewhere at the top of our first implementation file, we can just call this function. Put that closing bracket in as well, closing quote. And so what happens is, in this implementation file, when the compiler sees it, it'll look at this thing called say hello. It'll say, well, do I know what say hello is? Do I know what that means? And yes, it's seen the declaration of the function. It's seen this function declaration. So it knows that say hello is a function. It knows what argument types it takes. It knows it can take this, what's called a string literal, and make a standard string from it. So it knows that this function call is okay. It doesn't know exactly what this function does. It doesn't know the list of instructions it executes, but it doesn't need to know that. All it needs to know is its name, its parameter types, and its return type. So now later on, or somewhere else, we have a second implementation file, and I've run out of colours, unfortunately. I don't think that's I'm not going to take the risk that that's not a whiteboard marker. So we'll go back to red. But this is a third file now. So this is the declaration of the function. This is using the function. We've got one more thing we need to do. We need to actually define this function. We need to say, what does say hello do? So what we do to write a function definition is we repeat the signature, that is, return type, name, parameters. But instead of putting this semicolon at the end, we write a curly brace. And a curly brace is the start of what we call the body of the function. Its definition, what it actually does. And then we'll write what the function actually does. So in this case, we're going to return a new string. That's supposed to be one line. I'm not very good at this blackboard drawing thing. Return hello plus name. And then we close that. Well, be my guest. So these are two separate implementation files. One is calling the function, one is defining the function. And these can be passed to the compiler separately. They'll be in different object files. So the object file corresponding to this just knows that there's a function that we're calling. It doesn't know what that function does. This implementation file contains the definition. And then when later on we give these things to the linker, it will link up this call to say hello with the code to actually do whatever say hello does. Now the key point here is that if we change the definition of say hello in some way, let's say that instead of saying hello plus name, we'll put an exclamation mark at the end. So now we've changed the definition of say hello. So now it does something different. We haven't changed the signature of the function. We haven't changed its return type, its name, or its argument types, parameter types. So we don't have to make any changes to this implementation file at all. As far as this is concerned, nothing is changed, because all this implementation file knows is the facts: return type, name, parameter types. Those haven't changed. So we don't have to recompile this object file. We need to recompile this object file because we've changed what the function does. But we don't have to change this one. We can just link our object files together again. So we just need these magic files called headers that give us the signature, the declaration of the function. And then this magic of separate compilation happens. Yes?
So for like say, there's hundreds of files, you don't need one header file, which it contains all the functions.
So typically what you do is, for every implementation file, you'd have a corresponding header.
Right.
Yeah, and then, as we'll see, you can decide specifically which header files you want to be aware of. Comes under the section of using header files.
But then, what if, so in reality there'll be H1 and H2
Yes.
for those implementation files. So are they calling the same function? So you're then listing in each H file, H1 and H2, the same thing again and again and again, if you're calling the same function in each implementation file.
Let me go through this bit and see if you're still wondering. So there's this magic command, #include, that we can use in our implementation files to include a header. And there are two slightly different forms. We can either use it with the quotes or with angle brackets. The angle brackets mean this is coming from another library. The straight quotes mean this is from my own project. They do exactly the same thing, they just change where they look for headers. So with the quotes, it looks in the same directory as the current file. With the angle brackets, it'll look in the place where library headers go, which typically on a Unix system will be /user/include. Or, yeah, that's the usual place on Unix anyway. For Windows, it's a bit more complicated because everything is a bit more complicated on Windows. If you notice, there's a nice apple on the back of that laptop.
Catching virus is easier.
Sorry?
Catching virus is easier.
Yeah, that's pretty easy. Well, it's a lot harder than it used to be. Now, let me go on to the next one first. So, this #include command, it literally copies and pastes. It's literally what it does. Copies and pastes the text of the header into the top of your implementation file, or into the place where #include appears. So we can imagine that this is in a file called sayhello.hpp. Contains just this declaration. It tells us that a function named sayhello exists and the other information about it. And then in this implementation file, and again, I wish I had more colors because this is getting a bit confusing. Near the top of this implementation file, we'd say #include say hello.hpp. And what this would do, it would copy and paste everything from say hello.hpp into the top of our implementation file. Do you want me closing in this one?
Unflattering, like usual.
Yeah, thanks. So what it means is the declaration of this function will appear in the source code as if you had written this line in the place where you've put the hash include. So this include file mechanism is arcane and annoying, but it works and you do get used to it. So if you're coming from like the Java world and you're going, this is what's going on, this is a nightmare, then I get where you're coming from, and it's less than ideal, but you do get used to it, trust me. Header files, or this include system, can work recursively. So in order to use say hello, in order to use the function, well, you need to know what a string is. String is not a built-in type in C++. It's defined in a standard library header file. So we need to include that file. Every time we include say hello, we also need to include the string header so that when the compiler sees this funny standard string thing, it knows what that name means. So I've sadly run out of space on the board. So what I'm going to do, let's get rid of this and space things out a bit more nicely.
So standard string is basically like a built-in function, a class.
Standard string is a text file that you can, it's there on, the string header is a text file that you can look at on your system. And the string class is a type that's defined in C++. You could write your own version of, you could write your own string class if you wanted to. So we'll get on in a couple of weeks to how exactly you define your own types in C++. But in principle, if you wanted to, I wouldn't recommend it, but in principle, you could write your own string type of string. Standard string is the one that's written by the experts who wrote the standard library. So it's hopefully pretty good for use in most cases.
So if you know better, you can do it.
So I'm just going to write exactly what I had before. Well, nearly what I had before. There's a difference this time. What have I done differently? There's no name on it. Why have I left that out? Well, what are the important bits? What does the compiler need to know about the say hello function? 3 bits of information. Its return type, its argument types, and its name. It doesn't need to know the name of the arguments. It just needs to know the type. So in our declaration, we can just leave out the name. We don't need to put it in there. It doesn't really care what the arguments are called. That's not part of the signature. So really, yeah, we can put it back in there if we want. But in the declaration, that's really just documentation. It's not part of the signature of this function. Where's my red pen going? So I've done it a bit better this time. The header file's in green and the implementation file that uses this is in red. Okay. So imagine our implementation file now is the text in red. We first need to hash include the file say hello, this one. So this will literally copy and paste this text into there. So it will copy the declaration of this function into there. And then in this file, we've got a function, I just called it my function because I'm lacking imagination. And this function calls say hello, it passes it the argument Tom, and then it prints out the string that this thing returns. Now, as I was saying, if you want to use this function, just this by itself isn't enough, because we're going to copy and paste the declaration into here, and the declaration has these mysterious things called standard string, which is another type that we have to tell the compiler about. And so, in our header file, we need to include the string header. So the headers from the standard library are very special. They don't have this HTTP extension. And this is not our code, it's someone else's code, so we need to use the angle brackets. So it knows where to find this file. So what's going to happen now is it's going to try and copy and paste this file. It's going to look at this file and go, okay, well first I need to include string. And then we don't know what happens inside string. It's part of the standard library. We don't care. But probably that includes lots of files itself. So this including process happens recursively. Also, by the way, this isn't sufficient because we're using this cout functionality. So if we want to do that, we need to use another standard library header, which is called iostream. And now, finally, we've got something that works. How long have I got? 20 minutes.
The implementation is the missing.
Yeah.
In that example.
Right. Yes, so we have to imagine there is a third file somewhere else that contains the implementation of this. Or perhaps it's defined in a library.
Yeah. Can we bundle the implementation of say hello in the header file?
We
So
can.
Can we do that?
Yes, we can. You need to use a special keyword that's called inline to say that I'm doing this in one go.
Otherwise, could we generate the header file automatically from like a file that we had which had tons of...
Alas, not.
Okay.
Not yet. People are working on that. It's kind of tricky to do. What was the first? I was about to say
If we
something.
could bundle it in with the header.
Yes. So can we just write the function definition?
Yeah.
Can't we just write the function definition in our header and not have to worry about this? Yes, you can. You can write it what's called an inline function. And that will work perfectly well. The downside to that is that if we make any changes to our implementation, we now have to recompile every single object file that uses that implementation. So yes, you can do it, and yes, it's commonly done for some types of code, template code, but the downside to that is that we need to recompile everything. So if we make a change to the implementation of say hello, we might have to recompile 1,000 object files. Yeah?
You probably want an include guard in the header.
Yes. So header files. Header files can include other headers. Oh, sorry, was there a question?
Yeah, I had a couple of questions. Kind of mainly relates to how the compiler does certain things. So, first question is, you said that headers can reference each other.
Yes.
Could that create a reference cycle? if two headers literally reference.
Yes. Yes, it can. So that's exactly this point. We can have headers that almost recursively call one another. It's a problem. We need to make sure that we only have one version, or the header file is only seen once by the compiler. So to guard against that, we add what are called include guards to our header files. Now, for the most part, you don't really have to care about this. If you use CLion, these things appear automatically. The easiest way to do this is just at the very top of all of your source files, of all of your header files, sorry, is just to put this line #pragma once. And this says to the compiler, if I've already seen this source file, if it's already been included somewhere, skip it. Yeah.
Pragma once or if and def define. What is the correct way?
Okay, so the C++ standard, the strict definition of what the language is, doesn't include this pragma once thing. Okay, so technically you should do it using these things called include guards, if, not, def, whatever.
In def and if.
Yes.
Yeah.
However, every compiler that has been made in the last 20 years supports this. So you can do it either way, and they work identically. And certainly any of the big three, MSVC, CLion, and GCC, they all support doing this thing called pragma once. According to the letter of the law, it's not allowed, but that doesn't matter if everybody supports it. It's kind of de facto standard then, right? So if you do this pragma once thing, you might find that really pedantic people come along and go, oh, well, you're not allowed to do that. Ignore them. It's fine.
Can you not put all your includes in your header file and not fire about the CPP file?
You can. Yes, that's another way to do it. So you just have one mega header that contains all your includes, and you just include your mega header from all your implementation files. Anybody think of a downside to doing that?
Oh yes, because you want to include mostly classes in your header file rather than like iOS stream and stuff like that. Because it's easier, because then you know that your implementation file, what it needs. I think it's just easier.
Yeah. So the main downside to doing that, to having one mega header, is that anytime you make any changes to this header, you're going to have to recompile all your object files, which is exactly the thing we were trying to avoid.
Because when you compile together the header and the implementation file, you compile together. If you change one of the two, you have to compile both.
Exactly that, yes. So if we were to change this header, if we were to, let's say we add a new function to this header, which is called say goodbye. So now we've added a second function declaration called say goodbye. Well, now this header is changed, which means that every implementation file, don't forget, this implementation just copies and pastes this into the top of it. So that means that this file has changed. So we need to recompile this implementation file. It doesn't use say goodbye. It doesn't really care. It's going to generate the same object code, but it can't know that. All it knows is that we're using this header file. This header file is changed. Therefore, potentially we need to something may have changed that we care about. Therefore, we're going to recompile this. So whenever you change a header file, every implementation file that uses that includes that, has to be recompiled itself. Yes?
So would the compiler complain if there is a definition in the header but no implementation anywhere in the code, will it detect that and say like, hey,
The compiler won't complain because, don't forget, we send all our files individually to the compiler. All the compiler cares about is that we've got the declaration. You will get an error, but the error will happen later. The error will happen with the linker step, because the linker tries to resolve all of your function calls. It tries to say, okay, we're going to link this say hello call to the implementation, which is probably in another file called sayhello.cpp. It's that machine code is in a different object file. So it needs to link this call with the machine code that's in another object file. And if it can't find that, then you'll get a linker error. So it'll happen after. So remember, it's a two-step process: compilation first, then linking. If it can't find the corresponding definition, then you get a linker error.
no, but I was asking the opposite. If there is a definition but no implementation.
The header.
The definition is the implementation. You mean a declaration?
Well, if I let's suppose in our example, there is a say goodbye.
Yeah.
We have a definition of the
This is
say
a
goodbye function, but no implementation in any implementation file.
So this is a declaration. This declares that this function exists, right? A definition would be the one with the angle brackets, the implementation. So implementation and definition are the same thing. This is not a definition, this is a declaration.
Okay, sorry, I got the terminology.
Yeah. That's all right. It's very weird the first time you come across this, and that's why we're spending like a whole session going over this, because people coming from other programming languages, you go, oh yeah, functions, that's easy. Classes, oh, I understand those. This stuff about header files and separate declarations and definitions is really weird. And it's kind of unique to C and C++. So that's why we spend a bit of time going over it today. But rather than me wittering, it's worth me showing you a demonstration. So it's a little small, but I hope you can see it. Let's go down here. So we have our example project. We can see we've got main.cpp. We've got our CMake lists as well that I said you can look at if you want to. This declares a project called session 3 example. Tells us we're using the C++ 14 standard. And then we want an executable called session 3 example. And that executable is going to use this file main.cpp. So now to our project. We can right click, hopefully. Oh, it's just being slow. We'll go new, and we're going to say C++ source file. So we click that. I'm going to give it a name. Type is CPP. We're going to create an associated header as well. So we see we're going to create 2 new files, one called example.cpp, one called example.hpp. And you can see that it tells you what changes it's going to make to your CMake list file as well. So just click OK. It'll think for a minute. Probably quite a while because this laptop's being very slow. Now if we look at CMake lists, you can see it's put our new files as part of this executable target. These things, this is what I was saying about the include guards. You don't have to worry too much about what they do. Just know that you put your code in between the bit that says define and the bit that says endif. Your code goes in there. And then our example.cpp, we're including the header, but then we're not doing anything else just yet. So let's go ahead . And write a declaration of this function, say hello. Is this enough? Is this sufficient?
We need to include string.
I need to include string, absolutely. So what I'll do is I'll go up here. This is quite hard to do over my shoulder, by the way. Sting, include sting. I don't want to include sting. I mean, I'm a big fan of the police, but include string. That's better. So now we're including the standard string header, and we're declaring that this function say hello exists. And now in our main, we're going to include example.hpp. And now, if my laptop weren't so punishingly slow, you get all sorts of nice code completion and things going on, which hopefully I can show you in a second. Anyway, we'll go ahead and do it. In here, maybe, will we? There we are. Oh yeah, so CLion has hopefully collapsed down all our includes. So now we're going to call and we're going to say hello to Tom, and then we're going to insert a new line at the end. So this is going to say, this says we're going to take our output streaming object, we're going to pass it whatever the result of this function is, and then we're going to insert a new line and do other things. So we can try compiling this now. So now it's compiling two files. It's compiling separately our main and our example. And you can see it's making these .o files for us. And now the second step, so it's compiling the first object file, compiling the second one. Those happened at the same time. You get them happening in parallel. And then finally, once it's done all those, it tries to link them together. And at this point, it fails. So this is what you were asking me. What happens if we've got a declaration, but no definition? And we get an error. Neither of our compile steps gave us an error, but we got an error when we tried to link them together. And you can see it's got this horrible signature, but that's because basic standard string is actually quite complicated. You don't have to worry about it too much. But it's saying it doesn't know about this function called say hello. Doesn't understand, can't find a definition for this function. So let's write a definition. Name. If I could type, this would be a much quicker process. So now we're in example.cpp. And it's finally caught up with us. Say hello is redeclared with a different type. Standards. It's because I can't type string. There we are. And now we're just going to so we're going to return hello plus name. And it's not going to do it for us. There is a handy little icon here that you can flick in CLion. You can flick between the declaration and the definition. So CLion is smart enough to work out that there's a relationship between these, and it lets you very quickly go between one and the other. So now let's recompile our project. Press the play button. And now look at what it's doing. It's recompiling example.cpp. Oh. Where's that gone? It's recompiling our example file, but it hasn't had to recompile main, because main hasn't changed. We haven't edited this at all. So it didn't have to recompile main, it just had to recompile example. And then it linked everything, and this time the linker step worked happily. And we can see it printed, hello Tom, hello Tom.
Hello.
Hello.
Answer with the code.
Yes.
Could you show me a main file just for a second?
The main file is here. So the main includes the example header. So it copies and pastes this into the top. And that includes this line here, which is the declaration of the say hello function. Remember, its name, its argument types, and its return type. And then a semicolon afterwards says this is just a declaration of this function. In example.cpp, we put the same information, except this time, instead of putting a semicolon at the end, we don't do that anymore. This time, we have these curly braces, and we put what the function actually does. We put its definition in there. So we've separated the declaration of the function from the definition. And it allows us to compile things separately. And also, as you briefly saw, to compile things in parallel. We can have multiple instances of our compiler running at the same time. Greatly, if you've got, you know, a really beefy 64-core machine, this greatly speeds up your compiling. It's only the linking step that has to be done serially. So again, if your C++ is designed for writing really, really big projects, if you think about something like WebKit that powers a lot of web browsers, that's got tens of thousands of source files, you know, millions of lines of code. And C++ is designed for these really, really big systems. Again, the kind of AAA PlayStation PC games, they're going to have thousands of source files. And being able to do this separate compilation, to do everything in parallel, to not have to recompile the entire world when you make a tiny change, this is really powerful. So this thing of being able to extract the, could you automatically create headers? It would be lovely, but it has to be done very carefully in order to not destroy this model that, you know, works pretty well. So they are coming up with a system to do it. They're going to be something called modules, but it's been quite a tortuous process because they don't want to take away this thing that's pretty powerful as it is. So I'll just show you creating headers and source files in CLion. Basically, you right-click on you have the project layout on the left. You can right-click on the source file, right-click on the root of the project. Just go to New C++ Source. And when you do that, you can also click the box that says, please create a corresponding header. So I did have a little exercise for you to do, but it's 20:59, so we're going to have...
You have 60 seconds.
Yeah, so, well, not even that. You've got 32 seconds.
Is it? Okay, so even faster. Any hiccups?
Yeah.
Looking at what CLion compiles, the object that it compiles, so it looks like it's compiling one object per file. I mean,
Per implementation file,
yeah.
Yes.
Is that the standard way to do it, or sometimes it makes more sense to have one object per multiple files if they're related?
No, we have the correspondence is one CPP file to one object file.
Okay, so
that's it. Yeah. Okay, so if you want to take this away, that would be awesome. I will include a slightly more in-depth homework as well. This is not it, I'm afraid. Otherwise, you'd be done in a few seconds. If you just give me just a few seconds to finish up. So next time we'll be going back to, we'll stop talking about all this stuff about kind of build systems, and we'll go back to actually talking about the language. We're going to talk about value semantics, we're going to talk about object lifetime, we're going to talk about control flow, if statements and loops. We're going to actually start writing proper programs. So that'll be fun.
The next class will be very interesting.
Well,
from
I hope so.
C++ point of view.
I hope so.
No. I didn't mean this one was from C++ point of view.
Yeah. Anyway, thank you for coming. And if anybody wants to come to the pub, that'd be awesome.
Okay, thanks everybody. So just a couple of things before you set off. First, can you